video because section 3.2 is very long and I didn't want to make a 30-minute lecture or 45-minute lecture for our first video. I wanted to break it up a bit. So this section is on polynomial functions and their graphs. All right, so first let's recall what a polynomial function is. So a polynomial function of degree n is a function of the form p of x equals an x to the n plus an minus 1 x to the n minus 1 plus all the way to a1x plus a naught, where n is greater than or equal to 0 and an does not equal 0. So here's some explanation of what this means. So our an minus 1 all the way to a1 and a naught, those are our coefficients. All right, and I'm often going to abbreviate just as coef or coefs because coefficients is very long to write all the time. All right. And then here, this a naught, this is our constant term. It is the term that has no x corresponding to it. It's just a number by itself. All right, it's also called the constant coefficient. And then our next important term is this an. Just the an is called the leading coefficient. Whereas the whole an through xn, through x raised to the n, that whole term is called the leading term. So that's a breakdown of all of the important names within a polynomial function. So the important thing to know is that a polynomial, it's of the form of numbers times x raised to a different number, and they can all be added together. So there's no like x times y, there's no, I don't know if you guys have had trigonometry yet, but there's no cosine, there's no sine, it's just numbers and x raised to a power. That's what makes up a polynomial. All right. And then if we move forward, we can have an example. So if we have 3x to the 5th minus 7x to the 4th plus x squared plus 4x minus 2. So first thing to notice, this is a degree 5 polynomial. Our leading coefficient is 3. Where our leading term is 3x to the 5th. Our constant term is negative 2. And then now let's list out the coefficients. So there's a 3, there's a minus 7, and then if we look here, there's no x cubed term. So this implies that the coefficient here is 0. So we still include 0 in our list of coefficients because there's like a secret little 0x cubed right in here. Right? And then we have a 1 for the x squared, a 4, and then a minus 2. We also include minus 2 in our list of coefficients, even though it is not in front of an x raised to a power. All right, so that's our example. And then if we move on from here, if a polynomial has just a single term we call this a monomial. Mon for like one. Line that in yellow. Okay, and some examples of monomials is 3x, or x to the 5th, just the number minus 6, or something like 47x to the 9th. Okay. So now we're going to move on to graphing. So if we move on to graphing basic polynomials. So we can start with a graph everyone should know. This is the graph y equals x. So it's just a line. It's a line going through 0 here. This is the positive one, so it's positive where the inputs are positive and negative where the inputs are negative. And then another very common and important graph for this class will be a polynomial y equals x squared. So in this one, if you put in a negative value and square it, you will get a positive output, which is why the whole graph is positive. And then we can have this graph. Imagine that this little point actually went through 0. I missed it a bit. This is y equals x cubed. So it's if you look at it, it looks kind of like a line, the line graph where it's negative on the negative points and positive on the positive, but it's starting to get curved. And then we can have our fourth building block graph, just to give you an idea of how these things look and work. So this is the graph y equals x to the 4th. And now, I tried to draw this graph with a very flat, sort of like bottom to the graph. As each power of x gets larger, the part next to 0 gets flatter and flatter. So that's the main way to distinguish a large power of x versus a smaller one, is how steep or flat the bottom part is. So let me write a little note about that. So, and that's similar for the odd powers as well. Like x to the 7th would just be flatter around 0. So, as it also means that the parts further from 0 get steeper. So it's a little hard to tell with the graph drawn here, but after it hits 1, 1, this part of the graph, it's getting steeper faster than this part of the graph over here. All right, so now we're going to look at how to transform our building block graphs into more complicated polynomials. So we're going to start with multiplying by constants. So if we have f of x equals x cubed, then 6 times f of x equals 6x cubed. If we draw the graph, this is 1, 1, negative 1, and negative 1. I like to draw the points I know it goes through first because I feel like it helps me draw the graph better. So here's the graph of x cubed. So if we multiply by 6, that means the graph is getting stretched a little bit. So we're going to say this point is 6, and this point is negative 6. It's not perfectly to scale, but it will work just fine for the idea of how the graph works. So here, our graphs get kind of stretched up. It's like if you took an image on a Word document and you just grabbed the little top center bar and you pulled it up, the graph will get stretched like taffy up. And then if we were to have multiplied by a number like 1/2 or 1/3, that would squish the graph down. So that's how you multiply by a constant. And then another helpful constant to multiply by is -1. So if we have the same graph, f of x equals x cubed, then minus f of x will equal negative x cubed. And what this does to a graph is we have our original graph here. So multiplying by -1, it rotates around the x-axis. So our graph becomes this. So it means that if we take the output here, you multiply by -1. So it just flips it around this x-axis and it gives us the opposite outputs. So sometimes we won't just be by -1, it'll be like -6 or -42 is how we're scaling our graph. So it'll flip it and then stretch it. So that's how to multiply by constants. And then our next helpful tool is adding a constant. And we're going to call this one external, and you will see why in a moment. So if we have the graph, f of x equals -3x to the 4th, and we want to add 2, externally it'll be f of x plus 2. So that gives us the graph -3x to the 4th plus 2. So by external, it means we're adding it to the outside of our original function. So if we start with our initial graph, it looks kind of like this. And then we add 2. We move it up 2 points. So our new 0 point gets shifted up 2, and so do all of the other points. So our graph looks like this. So we've moved it up 2. Now, had we, instead of adding 2, had we subtracted 1, that would have shifted the graph down 1. So then our graph would have looked more like this. So by adding externally, we shift the graph up or down. Okay, so then our next helpful tool is adding a constant internal. Okay, so this means that if we have our function f of x equals x squared, and we want to add 1 internally, it becomes f of x plus 1. So we've added 1 to every x in our function. So then this looks like x plus 1 squared, which if we FOILed out would become x squared plus 2x plus 1. But we're still probably going to work with it in this form. I just wanted to show y'all what it would look like foiled. So if we draw our graph, it's our 0 point. So what happens when we add 1 internally, we shift it to the left 1. And you might think it's weird that we're adding 1, but now our 0 is at -1. So what this actually does, and a helpful way to remember it, is we need to think about the zeros. So the original 0 of our function was at 0 because x squared equals 0 when x equals 0, which is why we have it here. So then with our new function, x plus 1, this equals 0 when x plus 1 equals 0, which means that x has to equal -1. So that's why we have it here. If instead with our graph we had it be f of x minus 2, then we would shift to the right 2, 1, 2. And then this would be our new graph. So adding a number internally shifts it to the left, and subtracting a number shifts it to the right. So just really remember to think about where your 0 is. That's going to be the best way to really understand this adding a constant internally, because it feels a little funky at first. I used to get it mixed up a lot. And if you get it mixed up a couple times, don't feel bad. It's definitely a complicated thing, and it takes a little while for your intuition to catch up. So now that we have all of these tools, let's graph a more complicated function. So if we have f of x equals x squared minus 4x plus 1, so our first step is we're going to complete the square. Y'all should remember how to do this from 116. So we have that x squared minus 4x plus 1. This equals x squared minus 4x plus 4 minus 3. And then we are able to write this as x squared minus 2, or not x squared, sorry. X minus 2 squared minus 3. Okay, so I'm going to draw this in steps. So we're going to start with just the x squared function. So and we're going to subtract 2 internally. So that's our first one. I usually start with that one first because it's easier to do the external adding at the end. All right, and then we're adding or subtracting 2 internally. So we're going to go 1, 2, and it's going to get shifted over. So then this is our new x minus 2 squared graph. So then from here, we are going to subtract 3. So we move this 1, 2, 3. So then our new graph looks like this. So this is how you can do it. And if it's more helpful for you to do the steps as individual graphs and then have one final one, that is good. And when you're doing homework and we ask you to transform, just make sure that your final graph is very obvious so that when I'm grading, I can make sure I'm like, oh yes, this is the final graph. This is the one you meant to have. All right, so those are the steps on how to transform a graph and get to a more complicated one. I will record a new lecture soon and upload it, and I hope you guys are enjoying the beginning of a new quarter. All right, thank you so much.